Thank you. So, okay, everybody, put away your notebooks, put away your computers. We have a quiz. There's only one question. What do you see? And if you get it wrong, you fail. No cheating. What do you see? Anybody want to venture a guess? Yeah? Nope. Good guess, but wrong. You fail. Okay, don't worry. You're all in good company because computer vision systems also fail. Because current day computer vision systems have some kind of detector that they apply in a sliding window over the image at various positions and scales, sometimes applied to the output of proposal generation mechanisms. And very often, from inside the detection window, you can't determine what the object is. But if I open up the context, everybody in this room can recognize what the object is. What's important to recognize here is even though I opened up the context, you still actually cannot see the hammer in question, in this case because of motion blur. But to all of us, we have an incontrovertible percept of a hammer. How does that happen? In fact, if I open up the context even more, you can see the hammer. So there's got to be a lot more to perception than just detecting a pattern within a sliding window. And that's going to be the focus of my talk today. It's going to be the motivation for my talk today. I'm going to present a lot of different pieces of work, a broad overview of pieces of work, attempting to add context into perception. So object detectors, and there's been a lot of work on object detectors, significant advances over the past 5 years with convolutional neural nets. Many times they work. They can detect people and bags. But sometimes they fail, and they exhibit false positives, like they detect people on trees, and false negatives. They fail to detect bags. So how can we build a reliable ultimate processing system around an unreliable detector? So the general idea is that we can overgenerate. We can bias the detector to generate a plethora of false positives and use that to compensate for false negatives. And if we do that, we transform the detection problem into a selection problem. How do we select that single detection out of a plethora of overgenerated detections that corresponds to the object in question or of interest? And we can do that by formulating a lattice where each column in the lattice corresponds to a collection of detections in a given frame, and an attempt to form a temporally coherent track that composes information about the confidence of the detection produced by the detector, together with some measure of motion coherence, that is the degree to which the displacement of the detection in question corresponds to optical flow. And we can attempt to find an optimal path through this lattice by optimizing a linear combination of these two characteristics. And that can be done using the Viterbi algorithm. And if you do that, you turn an unreliable object detector into a selection process that can produce reliable tracks. And if we can do that, we can then extract features from the objects and tracks in question, such as their position and velocity and acceleration and aspect ratio and changing aspect ratio and area and changing area. And then also the detector itself is going to give us some information such as the object class, and perhaps we have some internal state of the detector such as the output features or mixture coefficients in the detector. And all of this can be fed into a process of processing the video in terms of a stream of detections. We also have activities that involve participation of more than one object detector. So for example, in this activity, we have an agent and an instrument, and we have relative features between pairs of participants, such as their distance and the change in distance and the orientation and change in orientation as a function of time. But very often, a single video can depict multiple activities. So in this case, not only does it depict a person riding a skateboard, but it also depicts a person approaching another person. And we can repeat this process for other activities, for example, the person approaching a person, or even the skateboard approaching the person. So if we can do this, we can get tracks over time and extract feature vectors and erect a hidden Markov model and use that to classify activity. And ultimately, on top of this process, we can build a video captioning system that produces textual descriptions of observed video. In this case, I've sped up the video so that it's not boring, so that the adjectives like slowly and quickly don't necessarily correspond to the video in question. But you can see we can produce semantically correct and coherent sentences that describe the video activity in question. And this is done not by stitching together captions that appeared in a training corpus, but rather by constructing individual words piece by piece that correspond to semantic features that have been extracted from the video, and then combining those together with a compositional process according to the grammar of language. So what I've shown so far is a staged process where there's an object detector followed by a tracker and followed by an event recognizer. But whenever you have a staged process, it is very, very brittle because errors earlier in the process can't be corrected later in the process. So we'd like to make this process not a single pipeline, but rather a joint process. And we can remove the barrier between these components and make this process more a joint estimation process. And I'm going to show that today for this part of the process. I also do it for this, but that's not the subject of the talk today. So the key idea behind making this process joint is the observation that the tracking process that I described previously is essentially an instance of the Viterbi algorithm as estimated by a lattice. But we can do that for a hidden Markov model as well. And if we do this as two cascades, we have two separate optimization processes where the output of the first, which is the track, is then fed into the second. And that leads to a one-directional processing pipeline. But if I make this lattice a cross product, what that does is it makes this optimization process a joint optimization process. And by doing that, I can have the event recognizer influence the tracker and vice versa. And I can still solve this problem in polynomial time by forming a cross product lattice where the nodes in the lattice are pairs of detections produced by the object detector and states of the event recognizer. And let me show you this in operation. On the left, you see a video where we're attempting to do tracking without any top-down knowledge of the activity in question, and we're going to track an irrelevant object because it is temporally coherent. But on the right, we're tracking in the context of an activity approach, where since the ball approaches the person in a second and doesn't approach the window, we focus the attention of the tracker on the participant in the activity in question. And that's top-down focus of a vision system from a language input. And we can carry this even further. We can have a collection of object detectors applied to a video, and then build a collection of trackers applied to those object detectors to detect the different participants in an activity, the agent, the patient, the referent, and the goal. And then we can have a complex sentence that delineates the activity in terms of specific combination of predicates applied to different subsets of the participants. So we can constrain the agent tracker, whatever it is, to be a person, and the referent tracker, whatever it is, to be a stool, and the patient tracker to be a traffic cone, and the goal tracker to be a trash can. These are all unary constraints. We can also constrain the agent tracker and the patient tracker collectively so that the agent carries the patient, which is an asymmetric relation. And we can constrain the agent and the referent so that the agent is left of the referent. And we can constrain the agent and the goal so that the agent moves towards the goal. And if we do this, we can formulate this as a collection of these Viterbi lattices where we have one Viterbi lattice for each of the event participants, tracking its position as a function of time, and one Viterbi lattice for each of the words in the sentence that represents the sequence of features extracted from the object detector that represent the semantics of the words in question over time. And we can constrain each of them relative to each other, and that corresponds to this large optimization problem. And again, if we did tracking independently of the semantics of the sentence, we'd have two independent optimization problems that we can ultimately ask for the summation of. But by moving the maximization outside and doing joint estimation, we can accomplish that by forming a cross product of all of these lattices, constrained so that they're linked together by the role assignment of which objects play which roles in which events. Yes? No. We are constructing each of these on a per sentence basis. Okay? And we have different lattices for different words in the lexicon, or different parameters for the output models and the transition functions for the lattices. We have different parameters for these based upon the objects that they're tracking, and they're linked together appropriately. And this entire thing here is constructed on a per sentence, per video basis. Okay? Yes?
I understand the lattice for object tracking, but what does a lattice mean in the case of event recognition?
So in the case of event recognition, I might have a complex event like pickup, which has two states: my hand moving towards the object in question, followed by my hand moving with the object in question away from its initial position. More complex activities might have larger number of states. Some things like, for instance, just a static property like person are just a degenerate case of a single state HMM. But since we formulate this all in terms of HMMs, we can form the cross product HMMs even though some of them are degenerate single state, and get just one large HMM which we can use then to do joint tracking and sentential comprehension.
Are the states supervised?
You're asking a question of how we train this process. Yes, we train it in an unsupervised. The number of states is supervised, we give it, but the delineation of the alignment of where the state transitions occur during training, that's unsupervised, and that's determined by the EM algorithm. And in fact, during classification, it's also done in an unsupervised fashion. That is, the Viterbi algorithm will automatically determine the state transition boundaries. Okay, so what we ultimately get is a single cost function that takes a video as input in terms of a collection of detections in each frame, labeled with whatever features we want to extract from those detections, together with a sentence, which is just a sequence of words, together with a lexicon, which is just a set of HMM parameters associated with each of the words in the sentence, and ultimately yields a score. That score answers how well does the sentence describe the video, or alternatively, how well does the video depict the semantics of the sentence. And as evidence of that descriptive process, it produces a collection of tracks which associate with each noun in the sentence a track in the video of a sequence of detections out of the pool of detections. This is just a scoring function. It's a cost function, and we can do multi-directional inference with this scoring function. And we can solve different problems. One thing we can do is focuses of attention. We can take a video as input, perhaps a complex video that depicts multiple activities occurring simultaneously, along with different sentences, and produce different collections of tracks that focus the attention of the tracker on the different participants that play the different roles in the sentence in question that are happening simultaneously in this video. We can also do generation. We take a video and a known lexicon as input and systematically search the space of all possible sentences to find the highest scoring sentence that describes that video. We can also do a video retrieval. We can take a sentence as input, a sentential query, along with a collection of video clips, and find that video clip which best depicts that query, essentially Googling for video. And then we could also do acquisition. We can take a corpus of video paired with sentences as input and wrap the entire algorithm with EM and then search for the lexicon that maximizes the overall joint likelihood of the corpus. We've done all of these. This last one was the topic of my ACL 2013 Best Paper Award. I'm not going to talk about that today. Instead, I'm going to talk about the first and the third piece of this. So here, we have focus of attention. And very crucially in the design of this small data set is we have videos that depict two simultaneous activities. And we're going to give two sentences that are minimal pairs that differ in only a single word. And we're going to thus produce two completely different collections of tracks with two completely different referents of the word person and the referent of the word object, distinguished only because they play different roles in the activity in question. Notice here, I haven't told it to track this person versus this person, or this object versus this object. It figures that out by the roles that they play in this sentential description. And I can then vary that for all words in the lexicon and for all sentential positions. And in doing this, I show that the system has deep understanding of each and every word in the lexicon and each and every sentential position as grounded in the video, because the differentiation of the word in question doesn't delineate, in and of itself, doesn't delineate the tracks that are produced. It's only the aggregate sentential semantics that delineates the object in question. So now we can also use this to do retrieval. So we started out by taking a Hollywood movie, in this case Quicksilver. The reason we chose Quicksilver is that in this video, people and bicycles and cars feature prominently. And at the time we did this predated AlexNet and convolutional neural networks applied to object detection. And we used what was then the state-of-the-art object detector, the deformable part model detector, pre-trained, unmodified on the Pascal VOC dataset. And the Pascal VOC dataset, cars and people and bicycles, are 3 of the 20 classes. We took the pre-trained, off-the-shelf detector and model and wrapped around it this sentential semantics framework and gave it the query, the person approached the car from the left. And the single highest scoring clip in the video, in the entire video, is this video clip. Then we gave it this query, the person rode the bicycle leftward. And the single highest scoring clip in the video is this. And then we gave it this query again, which differs only in a single word. And this single highest scoring clip in the video is this video clip. And then we decided to scale it up. So another class, object class, that features prominently in the Pascal VOC data set is horses. So we used the off-the-shelf pre-trained horse object model. And I asked my students to select Hollywood Western movies. And so we selected 10 Westerns. I don't know if you'd consider Blazing Saddles to be a Western, but nonetheless it has people and horses. And we did the same experiment with this data set, and I'd like to show it to you now. So what we've done is we've built a query engine, essentially Googling for video clips among these 10 Hollywood movies, which collectively account for about 20 hours worth of video. And what this is doing is not searching through any sentential annotation or any semantic annotation. This is actually searching, processing the underlying video to find collections of sequences of detections that exhibit a person riding a horse as a query. And we then annotated the entire video data set, and so 8 out of 9 of these are true positives, and 1 out of 9 is a false positive. So I'm going to just turn off the false positives so that we can focus our attention on the hits here. And we can take that query, and instead of doing rode the horse, we can say the person approached the horse. And we can get these hits. Notice here, the person is approaching the horse. Instead, I can have the horse approach the person. And notice here, the horse is approaching the person. I point out that these two clips come from the same scene of the same movie with the same objects, the same participants, and the same activity. One is approaching the other. And the only way we can distinguish between these two is that we know what roles the participants play in the activity in question. We can search for more complex queries, like the person rode the horse quickly, or the person rode the horse slowly, or the person rode the horse leftward, or the person rode the horse rightward. And we put up this system with all 20 movies, with all 10 movies, up on Amazon Mechanical Turk with an actual query engine, gathered sentences from anonymous disinterested parties, got the hits, put it up a second round to measure from anonymous disinterested parties whether the hits match the queries, and you can read the paper in PAMI that discusses the results. So the same general framework can be used to ground motor control in language, not just visual perception. Before I get to that, we'll get to that in a moment. We can carry this work even further. And there's a lot of recent interest in video captioning. And what video captioning systems do is take video as input along with object detections, either explicitly or implicitly, and produces output sentences. The reasons I say implicitly is that a lot of modern video captioning systems take a pre-trained deep learning network like VGG16 or Inception or ResNet that's pre-trained on ImageNet, which is a huge corpus of 14 million images that have been labeled and annotated. And then they take the prior to the last stage output, the FC6 or the FC7 features that are produced, and then feed that into some sequence model like an LSTM and generate captions. Inherent in that is a pre-trained object detector trained on 14 million images. What I'm going to describe now, I'd like to characterize as inverse captioning. We take a video as input along with sentences and produce detections as output. And crucially, there is no object detector whatsoever. No pre-trained object models, no training set, no human annotation. And the way this works is we have a very, very small code detection set that has videos paired with sentences. It's small. There's only like 15 to 25 such. And crucial to the design is that there's going to be some objects that co-occur. So for instance, a cabbage occurs here, and a cabbage occurs here. A bowl occurs here, and a bowl occurs here. And the word bowl occurs here and here. And the word cabbage occurs here and here. But the system starts out not knowing that the word bowl corresponds to this and the word cabbage corresponds to that. And it's going to figure that out. And the way it's going to do it is it's going to construct a graphical model. We're going to apply a proposal generation mechanism to generate candidate object detections in each video. This proposal generation mechanism is not going to have any object-specific information. It's going to apply just to low-level image characteristics like edges and texture. And we're going to over-generate and generate hundreds, if not thousands, of candidate proposals per video. And we have two kinds of edges. One kind of edge says, whatever we select as bowl 0 in this image, and whatever we select as bold 1 in this image, they must be visually similar. They must share some low-level image characteristics. Furthermore, we have similarity relationship between these videos. So between pairs of videos, we have similarity relationships, and within a video, we have semantic relationships. So whatever we select as cabbage and whatever we select as bowl must obey this sentential semantics that the cabbage comes out from the bowl. We solve this graphical model, and we're going to select the objects in question. It's a selection problem, selecting a needle in the haystack, finding that object detection that corresponds to the word in the sentence. And crucially, there is no background subtraction, no object detector, no object models, no per object class parameters. There's no learning except for solving this graphical model on a small collection of 15 to 25 videos, each labeled with nothing but a single sentence. Other than that, there's no training data, and there's no human annotated bounding boxes. What we do is we take a sentence like this, and we make no claim that we can completely and accurately reflect the semantics of the sentence, but we're going to convert it into something like this, which is a partial, incomplete, noisy representation of the semantics of the sentence, constructed with standard off-the-shelf mechanisms. The crucial thing is that these predicates are soft, they're graded, and some are unary and some are binary, which allows us to do inter-example, cross-example reasoning. We represent the semantics of the individual words with a very, very small collection of hand-constructed predicates. This literally corresponds to about 125 lines of C code. The Kolmogorov complexity of this description is considerably smaller than ResNet and smaller than VGG16 or AlexNet. So it's really not anything different than what anybody else does. But crucially, this has a whopping 3 parameters. The total number of free parameters in the system is over here. A small distance is a quarter of the field of view. A large distance is a quarter of the field of view. A small distance is 5% of the field of view. And an angle is pi over 2. I cannot fathom more generic parameters than this. The system is not sensitive to these parameters. You can modify them, and it doesn't change the performance in any drastic fashion. What we do is we generate proposals with off-the-shelf mechanisms and track them with off-the-shelf mechanisms and rotate them and construct the graphical model so that object instances that appear in the sentences, instances of objects that appear in sentences are vertices. The vertex labels are taken from tracks produced by the tracker, and edges between 2 object instances in the same sentences correspond to the semantics, and the clique for all object instances for the same noun are the similarity relations. And we use 2 standard feature extractors with 2 standard distance metrics for the similarity measures. Since there's nothing else out there at all like this to compare against, the best thing we can do is run the full model against various subsets of the model to measure how much each of the components contribute to the overall performance of the system. And so one of the models is going to remove all of this and just have, for example, motion detection through optical flow. Here's what the system looks like. Here are the raw proposals generated by the proposal generation mechanism. The vast majority don't correspond to the nouns in this sentence. Same thing here. We have hundreds per video. And it's again a question of selection, finding a needle in the haystack, finding a selection of a single proposal for each noun in the video that exhibits similarity across video and coherence with the sentential semantics. If all we measure is similarity across video, we get garbage, because this is similar across all the videos, this is similar across the videos. We don't get the objects in question. Same thing for this. Same thing for this. Same thing for this. This is state-of-the-art code detection in video. It doesn't work in this example. If we detect optical flow, we'll get the moving object, but not the stationary object. We get the moving object, but not the stationary object. We get the moving object, but neither of the stationary objects, not the pineapple or the coffee grinder. We get the moving object, but not the stationary object. If we do similarity in flow, we get the moving object, but not the stationary object. Sometimes we get both, but most of the time we fail to get some of the objects like the coffee. In this case, we get the pineapple, but we don't get the coffee. Here we get the cabbage, but don't get the bowl. If we do just sentences alone, we fail to latch on the objects, because this exhibits the changing spatial relations that correspond to the semantics of the sentence, but doesn't exhibit similarity between the objects across video collections. Same here, same here. We fail to get the pineapple. But if we use the entire cost function, we latch onto the objects in question. And I remind you, this is done without any object detector, without any per object class parameters, no pre-trained models, no training data, no human annotation of bounding boxes. Nothing more than a video paired with a sentence. Yes? The candidate object detectors are produced by MCG and edge boxes, which do not have any per object class parameters. They haven't been trained on labeled data. They operate purely on low-level image characteristics like edges and contour completion and texture similarity, but without any labeled training data. Okay? And definitely not for these particular classes. Okay? So here's an example. Here's some examples of how powerful the system is. Different objects in different environments, different people. Even when the objects rotate, even when there are two objects in the field of view, it knows which object is participating in the activity in question. There are cooler on top of the box. Here's the sentence, the sentential label over here. Even with a different data set that we took off the shelf, this is the CAD 120 data set that Ashutosh Saxena gathered. Even when there are three bowls, it knows which bowl is being put into which other bowl, or even when bowls are being taken out from other bowls. And even on the MPI cooking data set, which has objects that are very, very small in the field of view, it can determine which is the bread and which is the plate, and which is the bowl, and which is the bowl here, and the grater, and the plate, etc. So I'd like to move to the last part of my talk. I've been studying these processes in human perception as well. And I'd like to motivate this part of the talk by the following example. Here is a video and a natural language instruction. Jonathan, pick up the chair. What we observe in this is that the meaning, the semantics of the word Jonathan, whatever it is, at the input is distributed over a fairly wide portion of the field of view of the retina. So there are lots of neuron firings that contribute to the meaning of the word Jonathan. Likewise, the meaning of the word pickup, whatever it is distributed over a lot of neuron firings, both in space and over time. And likewise, the meaning of chair is triggered by a lot of neuron firings. Furthermore, some retinal points encode both Jonathan and pickup. So for instance, Jonathan is bending over to do the pickup, and that process encodes both the fact that it's Jonathan and the fact that he's executing a pickup operation. And some retinal points encode both pickup and chair. Like the chair is going to ultimately move upward. So those retinal points encode both the fact that it's a chair and the fact that it's moving upward. So the representation, the neural representation of the meanings of these words, at least at the retina, is a many-to-many, very diffuse encoding. Likewise, the neural representation of the output in the motor neuron firings is also a very diffuse, many-to-many representation. The question is, does there exist some point in the neural processing between the input and the output where the representation is more focused, more concentrated, less many-to-many, but more one-to-one? And that's a graded question, and we can quantify how much is it still many-to-many and how much of it has it been reduced to one-to-one. So ultimately, we ask the question is, to what extent does the brain employ a symbolic or intermediate representation? But that's too fuzzy, ill-specified a question. So I'm going to ask a set of 4 much more highly focused questions that are characteristics that we normally associate with a symbolic representation. 1 is that humans tend to make categorical judgments. That is, we decide that something is either John or Mary, but don't entertain a hypothesis that says it's 80% John and 20% Mary. To what extent is that reflective of brain processing? Second of all, we believe that semantic categories are modality independent. The question we ask is, to what extent is the same brain activity evoked when you see a picture of Jonathan, or you read the word Jonathan, or you hear the name Jonathan being spoken? Furthermore, the question is, to what degree is the mental representation factored? That is, to what degree is it the cross product of John or Mary walking or talking? And to what degree is it flattened as propositional, as in John walks, John talks, Mary walks, Mary talks? If it's this representation is exponential in this representation, and the question is, to what extent does the brain employ this representation versus this representation? And finally, the question asks, to what extent does the brain representation involve predication? To what extent does it represent the concept that it's John that's walking and Mary that's talking, as opposed to Mary that's walking and John that's talking? Which would not be the case if the representation were just a simple flat cross product like this. And these are specific questions we can ask and we can study and measure through functional magnetic resonance imaging. And that's what I'm going to show you now. I'm going to first attempt to provide some insight into this question. So most computer vision activity recognition systems take a video as input, process it by a computer to build a classifier, and get some accuracy as output. What's novel in the experimental paradigm that I'm going to show you today is we take the same video clips, but instead of showing them to a computer, we show them to a human subject undergoing fMRI. But instead of processing the video, we're going to process the output of the fMRI by a computer, and we're going to beat the pants off of existing computer vision systems. We're going to be able to read people's minds better than state-of-the-art computer vision systems recognize activity. And let me show you that here. We took an off-the-shelf data set. It's called Hollywood 2. For a long time, it was widely used for activity recognition experiments in computer vision. It's clips from Hollywood movies that look like this. And the objective is to label them with one of 12 classes, and then obviously in this case, the answer is KISS. And let me show you what the experiment looks like. Anybody here ever participated in an MRI experiment? So some people know what it's like. Quite a few people know what it's like. Okay? For those of you who have not, unfortunately I can't bring an MRI here and run a live demo, but imagine yourself lying on your back for hours and hours on end. You have goggles on your eyes, you're watching videos, you have earphones in your ears, you're listening to auditory stimuli, and all you have to do is think. And you see things that look like this. You think, hug, stand up, all of a sudden that comes along. Speech stimuli, but uncorrelated with a video. Just the spoken names of the 12 classes. And sometimes you see text. Uncorrelated with a video, just textual representation of the 12 classes. Randomly intermixed for hours on end. Answer phone. Eat. It changes in font and in point size and in position in the field of view to make sure that we're recognizing the semantics of the activity. And what we could do is if we just look at those stimuli that are video, we can do 1 out of 12 classification from brain scan data at about 60% accuracy. If we look at just those stimuli that correspond to text, we can do 1 out of 12 classification with about 50% accuracy. If we look at those brain scans for stimuli that are speech, we can do about 55-57% accuracy. If we pool these together, we can do about 35-40% accuracy. If we ask the question, can we determine from the brain scan whether the subject is watching video, hearing speech, or reading text, we can pin it to the ceiling. So you may ask, why don't we build this out of first applying this and then applying this? I'll get back to that question in a few minutes. But we can also do cross-modal classification. We can train a model just on video and then use it to classify brain scans of subjects reading text, sight unseen, and do way better than chance, like about 20%. We can train a model just on subjects reading text and then apply it to video and do way, way, way above chance. Same thing on video to speech, speech to video, same thing on text to speech and speech to text, all possible combinations. Some of them are down over here, like when you train on video. Some of them are over here, like when you train on text and speech. I'll get back to that in a moment. And here are computer vision systems, much worse than all of this. So here are the confusion matrices for reading out class from brain scan data of subjects watching video. It's highly categorical. For text, highly categorical. For speech, it's highly categorical. If you look at computer vision systems, it's garbage. Okay. So the results I showed you before were obtained by a support vector machine. And that's something that I coded up. One of the things that happens when you have smart, young, whippersnapper graduate students and they see a classification problem is they immediately say, I can do better. So I say, be my guest. I give them the data set. They go away for a couple of days and they try a new method, and lo and behold, they do better. Speech and language and computer vision for a very, very long time have had community data sets, community tasks where people march up the accuracy curves. That hasn't happened yet in neuroscience. I predict that it will happen in neuroscience. And when we do that, we're going to get better and better and better accuracy on brain readout and better understanding of brain processing as a result of that. I don't want to make too much of a deal about that, but the important thing about this is that a support vector machine classifies linearly separable data, and this is considerably lower than this because this data is not linearly separable. But our neural network is a two-layer network, and thus it doesn't have to be linearly separable, which is why we're able to move this number significantly above this and have it match this, which is essentially doing the first level classification of what modality and then the second level classification within modality. But we can go further than that. We can take either of these classifiers, the support vector machine or a neural network, and we can back project the internal model in these classifiers back to the brain volume, which ultimately is the input to these models, and determine which regions contribute most to the classification accuracy for a video classifier, a text classifier, and a speech classifier. And notice we see that there's overlap between red and blue and green, and ultimately overlap between red, blue, and green, which has to have been the case. There's no possible way you could have done cross-modal classification unless there was some overlap in the brain activity pattern evoked across modality. So we can quantify that. We can use a well-known method within computer vision, the intersection over union measure. In this case, instead of applying it to detection boxes in an image, we're going to apply it to back projected models onto the brain volume to determine the overlap of the brain regions involved in processing data of different modality. And if we do that, we see that the overlap between video and text is about 20%, between video and speech is about 20%, and between text and speech is about 40%. And again, that makes sense because text and speech are both linguistic, and video and text and video and speech are more cross-modal than text and speech. And that explains the difference in levels of cross-modal classification that we saw before. So what I showed you before are within subject classification accuracies. We can also do this cross-subject, that is, train a model on one subject or one set of subjects and use it to classify brain scan data on another set of subjects. While performance is degraded, it still is significantly above chance. If you take a step back and you think about it, what this means is that all of us in this room have some common shared representation that's shared across vision, speech, and language in the brain activity that's evoked on particular semantic concepts like run and sit down and stand up and the like. That somehow, despite all of our different language experiences and the different naturally existing corpora that we were exposed to by which we learned, we all managed to converge to the same brain activity patterns, or at least 40% overlap in the same brain activity patterns. And we can actually measure it. This is the overlap cross-subject in brain activity evoked from video response, the cross-subject overlap in brain activity evoked from text response, and the cross-subject overlap in activity for speech response. And again, these are higher, which is quite natural because these representations are more categorical than this representation. Okay. So we can carry this further and ask the question about cross products. To what extent does the brain represent a factored representation of information rather than a flat representation of information? And for this purpose, we can construct stimuli that are very carefully constructed as cross products of semantic concepts. One of four people doing one of three activities on one of three different objects in one of two directions or one of two locations. Very carefully constructed so that every person can do every activity on every object in every position of the field of view and in every direction. And we have a balanced design with the same number of stimuli of each form shown to all subjects in randomized order. And we can build classifiers to read out the subject, the verb, the object, the direction, and the location. But we also can build classifiers to read out pairs, actor-verb, actor-object, actor-direction, actor-location, verb-object, all possible combinations, and triples, all possible combinations, and even the whole sentence. And by doing this, we can ask, to what degree do the classifiers that represent flattened pairs and triples outperform or underperform the classifiers that construct the meaning of a sentence or of a whole video percept out of the individual components? And here's what the stimuli look like. Some of them are video, like Scott carrying the paper rightward, and Jeff leaving the chair leftward. Very carefully constructed so that they're all in exactly the same environment with exactly the same people and exactly the same objects and no extraneous objects, so that you can't possibly be triggering off of unrelated features, and you're triggering off of specifically the features that are related to this task at hand. If you give this data set to a computer vision system, it fails miserably because computer vision activity recognition systems and video captioning systems key off of irrelevant features. Sometimes there's text, again, that varies in font and in point size and position in the field of view. Complex sentences, or at least sentences that involve a subject, verb, object, and prepositional phrase adjoint. So we train two kinds of classifiers. One that are trained on the individual constituents, but tested by concatenation on pairs and triples, and others that are both trained and tested on pairs and triples. And what you see over here are the individual constituents, the green line is chance, and for the pairs and triples, on the left is the independent classifiers, and on the right are the joint classifiers. Sometimes the independent perform better than the joint, sometimes the joint perform better than the independent. But there's no statistically significant difference in the performance of one versus the other. That suggests that the brain is operating by using independent classifiers. But we can test that even further. We can do this just on the video stimuli, just on the text stimuli, trained on video, test cross-modally on text, and vice versa. Again, across the board, statistically massively significant results, way, way, way above chance. We can read out an entire sentence way, way, way above chance. And again, the confusion matrices are very diagonal. But we can ask the question. We have a stream of judgments produced by the independent classifiers and a stream of judgments produced by the joint classifiers. To what degree do these correlate? And it's very, very high. For text, for video, for text, cross-modally from video to text and cross-modally from text to video. We can ask the question, to what degree does the correctness of the judgment correlate between the independent classifiers and the joint classifiers? And again, it's way higher in all possible modalities. So this strongly suggests that the brain is operating with independent classifiers. That in perception and also reading sentences, it's not using joint statistics. It's not using a co-occurrence model. We can test this. We can, again, back project the models to the brain, and we get largely disjoint regions. Location is represented early on in the visual cortex. Direction is represented further downstream in the visual cortex. Object is represented in ferrotemporal cortex. Verb is represented here in the premotor cortex. And actor is represented here in the prefrontal cortex. Again, we can quantify this, and the degree of overlap across different categories is very small. But the degree to which the combination of the categories for pairs and triples and sentences is very, very high. Likewise for text, same thing. And we can measure the degree to which the information in video overlaps text. And it's very, very high. Again, it's between 30 and 40%. And we can measure the degree to which the representation is shared across subjects. And again, it's very, very high. Which shows that all of us here, when we're reading text, are constructing 40% common mental representations as when we watch video, and vice versa. Get to the last topic, and I'll go through this quickly. Ask about predication. We can repeat this experiment with active verb object pairs and triples, but this time we're going to do it twice in the field of view simultaneously. There's going to be Dan putting down a briefcase at the same time Scott is picking up a chair. And we want to determine from the brain scan data whether there's a difference between Dan putting down a briefcase, Dan putting down a chair, Dan picking up a briefcase, Dan picking up a chair, and whether we can determine who did what to whom when there are two simultaneous activities going on in the field of view and two sentences. So let me show you this. Here's what it looks like. Sometimes there are pairs of sentences that just have the adjoint on the left and the right. Sometimes one's above the other, sometimes reverse. Sometimes they both do the same activity on the same object. Sometimes Scott is on the left, sometimes Scott is on the right. Sometimes on the right is above, sometimes on the left is above. Sometimes the person on the left is not doing anything. Sometimes the sentence says that there's Dan in a chair, but there's no verb. Sometimes there's just a briefcase, but no person. Sometimes there's just a chair, but no person. Sometimes it's on the left, sometimes it's on the right. All possible combinations. There are about 128 different possible combinations. Sometimes they do it not so simultaneously. So we can read out the actor on the left and the actor on the right, way, way above chance. The verb on the left, verb on the right, way, way, way above chance. The object on the left, object on the right, way, way above chance. The pair of the actor and verb, the pair of the actor and object, the pair of the verb and object, and the entire sentence, all way, way above chance. From video, from text, and again, cross-modally, train a model just in video, test it on text, train a model just in text, and test it on video. We could read out an entire sentence, way, way above chance, even cross-modally. We can measure the cross-modal overlap, and it's somewhere between 20 and 40%. What this says is that the brain activity pattern evoked when you read a sentence, two sentences like John picked up the chair and Mary put down the briefcase, has 40% overlap with the brain activity evoked when you watch a video of John picking up a briefcase and Mary putting down a chair. And in particular, the brain activity pattern that reflects the linking between subject and object and verb has a 40% overlap with the brain activity pattern evoked when you determine which objects are being manipulated by which people in which activity. When you think about that, that's pretty astonishing. I'd like to summarize that there are two notable respectable enterprises, fields, engaged in two notable respectable activities. There's the field of AI, which is engaged in the enterprise of building intelligent systems. And there's the field of neuroscience, which is engaged in an enterprise of understanding how the brain works. A lot of people, for a very long time, have suggested that maybe AI can tell us something about how the brain works. I used to believe that. Having done neuroscience for about 4 years, I'm humbled. I no longer believe that. But I'd like to propose the opposite, that maybe neuroscience can tell us something about how to build intelligent systems. And I have a very concrete, tangible proposal. What people have done in psychology for a long time is they take data and they present it to a model and get predictions. And then they take the same data and present it to human subjects and get judgments. And the design of psychology experiments is you make sure that these are the same. You measure whether these are the same, and that provides some evidence as to whether these are the same. That's a little bit difficult because we know what's going on in here because we wrote the model, but we don't know what's going on in here. It's difficult to determine that, and that's why I'm interested in MRI, which is something you can't get from purely behavioral psychology experiments. And that will allow us to better answer this question. And let me show you a very concrete, tangible manifestation of this, a proposal. What I showed you before is that what computer vision systems do is present video to some feature extraction mechanism to extract a feature and pass that to some classifier to get class labels. The experiment that I did is I took video, presented it to a brain, got out features, got out voxels, passed those features to a classifier, and got out class labels. Very deliberately, these two systems are analogous. And very deliberately, we constrain the video to be the same. And we get different class labels. So somewhere here we went wrong. Where did we go wrong? Well, it can't be here because these two components are identical. So the problem must lie here. So whatever we use as feature extraction in computer vision just can't be as good as whatever the brain does. So a concrete proposal is that we can train this on to do this mapping. And we can only do this, train it to do this mapping because we have access to this data with MRI. See, most computer vision systems, this here is a latent variable. You have videos, and you have Amazon Mechanical Turk judgments, and you do end-to-end estimation, end-to-end training, treating this as a latent variable. But with MRI, we can present the same video to the system and get the internal human state of processing on the same data set. And then we can take this data and augment this data set and use it to train this data set end-to-end. And that is the research process that I'm engaged in. And I'll stop here and take questions. Yeah.
So in the first part, you mentioned that you didn't actually have a lot of human bounding boxes, labels on these things, but the model was picking those out from the unsupervised way. In the second, in the fMRI stuff, however, the humans are very good models. They're very good band detectors or spot detectors.
Yes.
So, do you have any sense for how those experimental results, the representation would change if you gave nonsense names to the people, objects, and those things? And did the same experiment, or it's just a different language or a made-up language?
Okay, so first of all, there are human subjects, and they're anonymous, disinterested parties as a result of the RB. They have never met the people who were used to film the video. They don't know who Dan is and who Scott is.
Those names are repeated.
Yes, but we never give them the correspondence. The only time we ever give them the correspondence is in the subject instructions at the beginning. We show them a single photograph of Dan and a single photograph of Scott that has the label Dan and Scott.
Yeah, I guess I'm kind of curious what would happen if the language changed on every input, so that the person had to try to do the inference just based on the representation of picking up or what.
Yes, that would be an interesting experiment. And thank you for the suggestion. I hope to conduct that experiment. We can also ask the question cross-language, cross-linguistically. What if I have the text in different languages? What can we do? We can also ask cross-modally, what if I have the language, some of which is text or spoken language, and some of which is sign language? Do the same results hold? Yes.
You left out the important comparison. You framed the research question. Do we actually have, if Mary picks up a chair and John folds a piece of paper, then does the brain respond equally well to that pair of sentences versus John picks up a chair and Mary folds a piece of paper? But you didn't actually show us that comparison. Have you done that yet?
Oh, so we have the data to do that. And that's reflected in the accuracy measures. But for a particular cross-modal comparison, we haven't done that. But yeah, that's just a question of analysis now. Or cross-argument associations, yes. That's a very good analysis. I haven't done that, but I'll go and do that, yes. We have the full set of data. It's just a question of redoing the analysis.
That would be great to
Yeah.
sort of prove that there's something other than bag of words going on in the fMRI data.
Yes.
All right, this thing, Jeff again.